Okay, so now I found the page. This is page 23, equation 154. That's a Lorentz number. Okay, then the Lorentz number we just saw was actually, instead of 3/2, it was pi square over 2. Okay. And this says equation 153 gives a Lorentz number of 1.11, which is about half the typical value given in table 1.6. In his original calculation of the electrical conductivity, Drude erroneously found half the correct result, 1.6, as a result of which he found the value kappa over sigma t equal 2.22 times 10 to minus 8 watt-ohm Kelvin square, watt-ohm per Kelvin square, in extraordinary agreement with experiment. Yes. Drude found the value 2.22 is this value. Drude found the value to 2.22 by mistaking factor 2. Okay. And the value in Sommerfeld's theory was 2.44. Let's see. 2.44 is also not bad. 2.44, not bad. Actually, I don't think it's so bad. 2.44, 2.44, 2.44. 2.44 is better, I think. Okay, so let's go back. I need an announcement. Let me see. Okay, so we are here. This sentence. This is remarkably close to Drude's fortuitously good value, thanks to the two compensating correction of order kBt divided by epsilon f. So this one. Drude value was good, thanks to the two compensating correction of order kBt divided by epsilon f. And in excellent agreement with the data in table 1.6. Okay, now I know this is 1, not 2. We shall see chapter 13 that this value of the Lorentz number, so this is this value of the Lorentz number is a far better one. Far better one than the very rough derivation of 293 would suggest. Anyway, strange. I would say just strange. Don't worry, we go next. Thermal power. Drew's overestimate of the thermal power is also resolved by the use of Felby-Dirac statistics. Substituting the specific heat from 281 into equation 159, we found thermal power Q equal minus pi square divided by 6 kB divided by E times kBT divided by epsilon F, EF, which is minus 1.42 times kBT divided by epsilon of F, decorated epsilon of F times 10 to the minus 4 volt per Kelvin, which is smaller than Drew's estimate 160 by order kBT divided by epsilon F, which is 0.00 at room temperature. Let's see, what was 160? What was 160? Let's see, let's go 26. Okay, he got minus kb divided by 2e. kb divided by 2e. kb divided by 2e. Okay, so what he found is this. This is Drew's value. kb divided by 2e. This is Drew. So, but this value is more like 3/2. So this value is like 3 times. This is 3 times Drew. 3 times Drew times this factor, which is 0.01. Okay. Other properties. Since the form of the electronic velocity distribution did not play a role in the calculation of the DC and AC conductivities, is that right? Since the form of the electronic velocity distribution did not play a role in the calculation of DC or AC conductivities, the Hall coefficient or the magnetoresistance, the estimates given in chapter 1 remain the same, whether one uses Maxwell-Boltzmann or Fermi-Dirac statistics. Hall coefficient or magnetoresistance estimate. This is not the case, however, if one uses an energy-dependent relaxation time. If, for example, one thought the electrons collided with fixed scattering centers, then it would be natural to take energy-independent mean-free path, and hence the relaxation time tau is L over V, which is L over epsilon to the power 1/2. Shortly after Duluth set forth the electron gas model of a metal, H.A. Lorentz showed, using the classical Maxwell-Boltzmann velocity distribution, that energy-dependent relaxation time would lead to temperature dependence in the DC and AC conductivities, as well as to non-vanishing magnetoresistance and field and temperature dependent Hall coefficient, as one might now expect from the inappropriateness of the classical velocity distribution. None of these corrections will in any way be able to bring the discrepancies of the Duluth model into better alignment with the observed facts about metal. Furthermore, we shall see, Chapter 13, that when the correct Fermi-Dirac velocity distribution is used, adding an energy dependence to the relaxation time has little significant effect on most of the quantities of interest in a metal. If one calculates the DC or AC conductivities, the magnetoresistance or the Hall effect coefficient, assuming energy-dependent tau of epsilon, the result one finds are the same as those one would have calculated assuming an energy-independent tau equal to tau of epsilon f. In metals, these quantities are determined almost entirely by the way in which electrons near the Fermi level are scattered. This is another very important consequence of the Pauli exclusion principle, the justification of which will be given in Chapter 13. Footnote: the Lorentz model is, however, of considerable importance in the description of semiconductors, Chapter 29. The thermal power is a notable exception. These assertions are correct to leading order in kBT divided by epsilon f. But in metals, this is always a good expansion parameter. These assertions are correct in leading order in kBT divided by epsilon f. But in metal, this is always a good expansion parameters. But why but? These assertions are correct to leading order in kBT over EF. I wouldn't use but. I would just say in metals. This is always a good expansion parameter. Let me see. Let me check again. Other properties. Since the form of the electronic velocity distribution, electronic velocity distribution did not play a role in the calculation of DC or AC conductivities, the whole coefficient or magnetoresistance, or the magnetoresistance, the estimates given in Chapter 1 remain the same, whether one uses Maxwell-Boltzmann or Fermi-Dirac statistics. This is not the case, however, if one uses energy-dependent relaxation time. If, for example, one thought the electrons collided with fixed scattering centers, then it would be natural to take an energy-independent mean-free path. Hence, the relaxation time tau equal L over V, which is L over epsilon to the power 1/2. Shortly after Duluth set forth the electron gas model of a metal, H.A. Lorentz, there's a T. This is Lorentz. This has T, right? But the Lorentz in Lorentz number doesn't have T. Okay, this one. This Lorentz, no T. This Lorentz number, no T. But new Lorentz, H.A. Lorentz, this has T here. Showed using the classical Maxwell-Boltzmann velocity distribution. Using a classical Maxwell-Boltzmann velocity distribution, that energy-dependent relaxation time would lead to temperature dependence in the DC and AC conductivities, as well as to non-vanishing magnetoresistance and field and temperature dependent Hall coefficient, as one might now expect from the inappropriateness of the classical velocity distribution. None of these corrections will in any way be able to bring the discrepancies of the Duluth model into better alignment with the observed facts about metals. Lorentz model is, however, of considerable importance in the description of semiconductors. Thermal power, 32. Furthermore, we shall see, chapter 30, that when the correct Fermi-Dirac velocity distribution is used, adding energy dependence to the relaxation time has little significant effect on most of the quantities of interest in a metal. Thermal power is a notable exception. If one calculates the DC or AC conductivities, the magnetoresistance or Hall coefficient, assuming energy dependent tau of epsilon, the result one finds are the same as those one would have if one calculates the DC or AC conductivities. The magnetoresistance or Hall coefficient, assuming an energy-dependent tau of epsilon, the result one finds are the same as those one would have calculated, assuming an energy-independent tau equal to tau of epsilon f. In metals, these quantities are determined almost entirely by the way in which electrons near the Fermi level are scattered. These assertions are correct to leading order. In kBt divided by epsilon f. What is leading order? What is leading order? But, why but? These assertions are correct to leading order in kBt divided by epsilon f. But in metals, this is always a good expansion parameter. In metals, this is always a good expansion parameter. わかんない。I'm sorry, I don't understand. This little significant in most in metal, these quantities are determined almost entirely by the way in which electrons near the Fermi level are scattered. In metal, these quantities are determined almost entirely by the way in which electrons near the Fermi level are scattered. This is another very important consequence of the Pauli exclusion principle, the justification of which will be given in chapter 13. In metal, this is always okay. I don't understand. Sorry. So let's go to problems. The free and independent electron gas in two dimensions. What is the relation between N and Kf in 2 dimensions? What is the relation between Kf and Rs in 2 dimensions? Prove that in 2 dimensions the free electron density of level G of epsilon is a constant independent of epsilon for epsilon larger than 0 and 0 for epsilon smaller than 0. What is the constant? Okay, show that because G of epsilon is constant, every term in the Sommerfeld expansion for N vanishes except that T equals 0 term. Deduce that epsilon mu equals EF epsilon F at any temperature. Deduce from 2.67 that when g of epsilon is as in C, then mu plus kbt logarithmic something is EF, epsilon F. Estimate from 295 the amount by which mu differs from E of epsilon. Comment on the numerical significance of this failure of the Sommerfeld expansion and on the mathematical reason for the failure. Okay, I think we are doing number 26, right? Did I announce? Seems I did announce. Yes, okay. I did announce. This is 26. Then two-dimensional. How should we do two-dimensional? Two-dimensional electron gas. Don't understand. N and K in two dimensions. Okay, we assume spin degree of freedom by multiplied by 2. So Kf, okay. Kf, what is Kf? Kf in two-dimensional. K space is two-dimensional. So this is the Kx, Ky. And Fermi sphere become Fermi circle with radius Kf. Okay, so we have the area is pi Kf square. Then how many electrons are there with Kf? Is it L divided by 2 pi square? Correct? I think this is correct. Yeah. 2 pi L over 2 pi. This is like so you have many allowed levels of electrons. And this is 2 pi over L. So I'm wrong. So this is so this is 2 pi over L. 2 pi over L square times 2. This is speed. That's L. N. This is speed. Actually, this is not N, but this is large N. Okay, so this should be okay. So then, from which we find this L go to here, L square. Okay, so 4 pi squared 2 pi kf square. This is n. So kf square is 2 pi n. This is the answer. What is the relation between kf and rs in 2 dimensions? rs. Okay. rs. We can do rs this way. So we have, let's see, these are n atoms. So this is F. Right? So V over N. This is, I'm sorry, I don't think we should use V. This is area. This is area. Or S. L square. So, okay. This one we define. Then should I divide by, so we should divide this by 2. See? I don't know. I will do this way. And divide by 2. Because we have spin up and spin down. If we consider 1 electron from 1 atom, this is my assumption. 1 electron from 1 atom. No. Yes and no. 1 electron this is okay. 1 electron per from 1 atom. Okay, so okay, we just do 1 electron from 1 atom. So then this is 2 pi rs square. Pi rs square. Yeah. This is n. 1 over n. So what is the relation? This is kf square 2 pi. This is kf square 2 pi. So we can cancel pi. Kf square 2rs. This is the result. No. I'll do this. KF RS equals square root 2. KF RS equals square root 2. Yeah. Let's see solution. AshcroftMermin solutions, which is better? Let's see the first one. No solution, chapter 2. Okay. This one. Chapter 2. N equal kf square is 2 pi n. That's what I do. Kf square is 2 pi n. Okay. Second one. Yeah, this is right. Kf Rf equals square root 2. Kf Rs is square root 2. Part C. Prove that in two dimensions the free electron density of level G of epsilon is constant independent of epsilon. Okay, so this is okay. I have this one. We just use this one. Let's see. I can just show equation how to calculate. I can just show how to calculate. K square is 2 pi a n. N of k. Then I can do this. K square. Okay. Let's see. I can do this one. This k square, I convert E equal h bar square k square 2m. So k square equal 2e divided by h square. So this is like this. H square 2me equal 2 pi n. Let's use this n of e. So you can cancel. 2. Then how do we? Pi. Let's see. I can go up. Pi m h bar square I'm sorry, pi downstairs. Pi and me equal n of e. And density of levels. Was it density of? Density of levels. Okay. Density of levels. This is partial ne partial e. So this is like this. Pi h bar square. This is the value. For epsilon air energy is larger than 0. If energy is smaller than 0, it's 0. So let's see the solution. Solution is this one. G equal m over pi h bar square or g equals 0. Show that because g of epsilon is constant, every term in the Sommerfeld expansion for n vanishes except t equals 0 term. Deduce that mu equal epsilon f at any temperature. Sommerfeld expansion. What is a Sommerfeld expansion? This one, Sommerfeld expansion. Or this one. Okay, let's see the solution. Since g is constant, g prime is 0, all the term in the BS expansion. Is Sommerfeld expansion? What is BS expansion? We apply the Sommerfeld expansion. Sorry. All the terms in the BS expansion are equal to 0. We find n n. Okay, we consider carrier density n. That's same as zero temperature value, okay, because this is zero. If we consider carrier density, then because this is zero. Okay, and mu. Mu, we have to find mu. I don't understand this. I don't understand this. Oh, handwritten. We go to 277. We go to 277. Oh, We apply this expander to the integrals in 271 and 272 and replace mu by EF in terms already of order t square in this equation we find. Oh my god. Anyway, let's do next one. Deduce from 267 that when g of epsilon is as in C, then this is correct. 267 with 267. 267. Sorry, I don't remember the problem. I don't understand this. Mu plus kbt log. Okay. This is we can do this way. So this is the view, right? So then we have mh bar square. Pi h bar square m. That's the density of states, density of levels, right? So then we integrate. So this is a constant. We just integrate Fermi function. Fermi function is something like this. Exponential, let's call this e. E minus mu divided by kbt plus 1. So we integrate 0 plus infinity e dE. So the question is how we make this integration. Do we use any approximations? You can see here. I think we can change. This is more like this. 1 plus epsilon minus mu kbt equal exponential EF minus mu divided by kbt minus, is this correct? EF, no, EF, we don't need EF, I think. We don't need minus, because this inside bracket, this is this, and EF minus mu divided by kbt, then exponential. Yeah. So how do we do this? I don't know. Is this correct formula? Log.2 かけるうーん Okay, so let me see. This is more like this. This is equal EF. EF. Can we calculate something like this? Can we calculate minus infinity to 0 exponential e minus mu divided by kbt? Let's make some approximation. let's try some approximation. Plus 1 this. So because this guy is very large, no, this guy is very small, d. Let me just do this 1 minus this. Let's do this one. Then okay, this is the same as having e minus mu divided by kt. Okay, so this is like this, minus infinity to infinity e minus mu kbt dE. Okay, so this is like this. kbt exponential e minus mu minus infinity to infinity. Is this right? Divided by kbt. Because if you differentiate, you have kt. Okay, so this is correct, I think. It's 0. So this is kbt exponential minus mu divided by kt. So this is like m. No, this is like pi h bar square m times mu minus ef. So there is no mass. There is no mass. Let me see. Okay, I understand. Strange. Okay, so I accept we don't need this, but then it's a little bit strange. take log. So kbt log. Okay. So I take this can be reversed. This is EF minus mu. Okay. Then all we have to do is this is actually logarithmic 1 plus exponential minus mu kbt. So let me see. I want to stop it now. We can continue next time.